Welcome to week 10. Hopefully, this format will work out well for you. I decided that given the nature of this class and how it sort of operates, and the quizzes and times you spend looking things up and doing labs, and with the holiday coming up this week, I felt that by providing you your lecture in this format, and giving your assignments, and if you haven't noticed, all of the assignments from this week are have been kind of extended out a little bit longer than what they normally would be. The idea is that well, your quiz this week will have a few extra days on it, because I don't want you to get too caught up and get behind trying to keep up with deadlines as the semester comes to an end, dealing with a holiday and potential travel and family commitments and all that kind of stuff. So I figured this would give you an opportunity to watch the lecture whenever it was suitable for you, even if that is during the regular class time. But more importantly, give you a little bit more flexibility over the course of the week, and hopefully that would help you enjoy your Thanksgiving season. So, again, stuff by the publisher. And Chapter 8, we're going to talk about spatial analysis of vector data. So a couple of things we're going to try to do here is become familiar with some of the basic concepts of things like single overlays and such, and to become familiar with how we implement some of these basic processes and what it all means. So first we're going to talk a little bit about single layer analysis. This is things like buffering and geoprocessing. And buffering is really just placing a region of specified width around a point, a line, or a polygon. It is an area defined by a distance from a thing, essentially. Whereas geoprocessing is any operation that is used to manipulate spatial data. So it could be a buffer, it could be a lot of different things. Let's talk about buffering. Constant width buffers are the most basic, easiest to sort of understand. They're simply regions of constant width around points, lines, or polygons. But that's not the only type of buffer. You can have variable width buffers, regions of which are simply regions of variable width around points, lines, or polygons. And you think about something like that. Why would you do that? Well, you could have a buffer that is related to some variable about the entity that you're buffering. And so based on the information of that entity, it could change your buffer. You can also have multiple ring buffers. Think of like a bullseye target, multiple concentric regions with a specified width around points, lines, or polygons. You have a donut buffer, which is a buffer around a polygon feature that does not include the area inside the buffered polygon. And then you can have setback buffers, which is a buffer around a polygon feature that only extends inside the polygon boundary. So it's kind of like an inverted buffer, if you will, or a buffer of a negative distance to a polygon. So instead of being so far out, it's so far in. So here are some examples of what we're talking about. Buffers are the tan, around the features are the red, points, lines, and polygons. Additional buffer options around features. We look up here at A and B and C and D, E and F. A is pretty straightforward. Variable width. I would imagine what we're looking at here is different types of roads, and certain roads have a larger buffer than others, and I'll give you a real world example. A lot of people don't realize this, but if you look at your average run-of-the-mill road, paved, state-maintained road, the land that road is on doesn't really belong to the state per se. It belongs to some person, or at least it did. And usually they claim that property, or the property is donated or given to them one way or the other. The property of the road becomes communal property, public property, however you want to view that. But it gets a little bit more complicated than that. You see, at the edge of the road does not end the property that the road has reasonable expectations and access to. And so they call it a right-of-way. And essentially what it means is there is a feature over the property that exists to a certain width. It's typically measured from the center of the road. And that is the property that is assumed to be the road. Even though it's not part of the road, it's part of the land along the side of the road. Different types of roads have different right-of-ways. Some right-of-ways are really restrictive and they literally only cover the road space itself. Others are a little more generous because they know certain types of roads have need and require need of additional space along the sides for equipment when they're doing things with the road, for drainage, ditches, and things like that to be put in place. And so there might be a 40-foot right-of-way on one type of road and only a 30-foot right-of-way on another type of road. They both could be the same sort of two-lane style road, but one has a larger, sort of a gravel median or pull-off area along the side, a shoulder, if you will, and one may not. It could have everything to do with who maintains the road, the amount of traffic on the road, or any number of things. But that could literally be a buffer like this, like A, is translating that right-of-way component to show the actual area that the road is responsible for, as opposed to the simple line. B is those concentric rings, or a multiple ring buffer. I'm sorry, B is rather. C is a donut buffer. And what is a donut buffer? That is, let's see, that is a buffer around the outside that does not include the inside. So the buffer is only exterior of the polygon. And then D is a setback. In other words, it's an inward facing buffer. It's a buffer that is on the inside of the polygon to a set distance. E and F are two other common things we need to understand about buffers, particularly when we buffer around features, multiple features. You'll get occasion where buffers will overlap, and you have to make a decision when you're doing this sort of work. Do you want those individual buffers, or do you just want to have all the buffered area collectively together? And so if you want individual buffers around each feature, then you don't dissolve the buffers. And so it treats each one as its own little entity. But if you dissolve the buffers, if, for example, like you see these three circle buffers around these points overlap, where they overlap, it just essentially does a union and keeps everything that's common to all of them. And you end up with F. So let's look at a couple terms here. Dissolve. It's a geoprocessing technique that removes the boundary between adjacent polygons with identical values. Append. Append is a geoprocessing technique that combines adjacent polygon datasets into a single dataset. Select is used to define a subset of the larger set of data points or locales. Merge is to combine adjacent or overlapping spatial features into a single feature. I take a little bit of a position relative to their definition of append. Append is more like when you add additional data into an existing data set. Or more appropriately, when you add one additional data set into another additional data set. Whereas merge is when you take two individual data sets and combine them to create a third single new data set. So here we can see dissolve. Notice that you've got some 1s, some 2s, some 3s, and some 4s in A. If you dissolve, all the number 1s become number 1s as a single entity if they can be dissolved as such. So those two polygons labeled 1 that are coincident, the coincident boundary goes away and you're left with that polygon. Same way with the number 4s, where the 3s are not together, they're not coincident in any fashion, they remain in their own position. Now, if you were to look in the attribute table of A, you would have a row for each of those polygons. Both of the 1s, the 2, both of the 3s, and both of the 4s. In B, after you run the dissolve function, while you have two polygons there that are numbered 3, you would only have one entity in the attribute table that would list it as 3, because even though 3 is two places, it's just a multi-part component of the same thing. Append is, like I said, two data sets, and it takes the second one and adds it into the first one, and you end up with what you see there as the third. Select 1 out of A in C, and you get B inside of C down there at the bottom. Let's talk about some key terms. Overlay. The process of taking two or more different thematic maps of the same area and placing them on top of one another to form a new map. That's the most general way of thinking about this from a map standpoint. I tend to think more about it in terms of data layers, but it's still a valid way of explaining it. And it would look kind of like this. Map overlay combining information from points, lines, and polygon vector layers as well as raster layers. And so a simple map overlay just stacks up all the things that you know and all the stuff that you have together. Now, these overlays can be a little more complicated than just looking like they're stacked on top of one another. We're going to talk about a couple different types of overlays. First, we're going to talk about point in polygon overlay. It requires a point input layer and a polygon overlayer. Upon performing this operation, a new output point layer is returned that includes all the points that occur within the spatial extent of the overlay. So the diagram here explains it. You've got point in polygon overlay. You've got point number 1, you've got point number 2, and you combine that with polygons A and B, and so you get A1 and you get 2B. So the point data gets the attribute and other information from this overlay. Polygon on polygon on point rather, is different. It will then take the information from the point and add it to the polygon in your output. Line on line requires line features from both inputs and the output layer. The output from this operation is a point or points depending on the situation, and it occurs wherever there are intersections of the two linear features. Line and polygon. You have a line, crosses a polygon, and you can see what happens there. Polygon on polygon. polygon on polygon overlay, polygon input. These are not as groundbreaking as what maybe you're hoping for, but it's really just simple ways of thinking about what happens when I try to overlay this with that. Now we can also do multiple layer analysis. This is things like union and intersect and symmetrical differences and identities, and these are often physical manifestation of specific terminology like and or. These type of operators allow you to do things. For example, the or function. If you have a polygon A and you have a polygon B and you do a union between A and B, and you use the or function, so it's A or B, your output is everything that's in A and everything that's in B, because everything that's in both of those is either in A or B. Intersection is different. That's the and function. You have two polygons, A, and you have polygon B, and if you use the and function, A and B, only space that is common to the areas of polygon A and polygon B would be selected from the intersection. Symmetrical difference is kind of one of those unusual ones. I'm not going to spend too much time talking about those now. You will learn to do those in GIS 200 and 201. Identify creates an output layer with a spatial extent of the input layer, but includes attribute information from the overlay. So here are some vector overlays. So we've got our features here, and when we do a union of the two polygons, bars and the circle, you see what you get. When you do a union, or sorry, an intersect instead of a union, you only get the common space to both data sets. Symmetrical difference, you only get data that is in either one but not in both. An identity is simply one but with some of the confining elements of the other. We also have a couple other functions that we use a lot. Clip, erase, and split are pretty common. Clip essentially trims a data set. It's like a cookie cutter. You take another layer that's your clip layer, and it simply just defines the space from which you're going to remove information from the original input, and that becomes your output. Erase is sort of the opposite. I liken clip and erase to making cookies. Your inputs is your cookie dough, your clip layer is your cookie cutter. Clip gives you a cookie, erase gives you the sheet of cookie dough after you remove the cookie. Split uses one feature to essentially split another feature, and that's what that does. Clip and erase and split don't maintain any attributes from the clip layer. They simply chop up the input layer. The input attributes will still be there, but nothing from the clip. Clip geoprocessing is used to extract features from points, lines, polygons that fall within a spatial extent. Erase, and I just went over that. I'm not going to read it again to you. All right, let's talk a little bit about this concept of a spatial join. Spatial join is a hybrid between an attribute operation and a vector overlay operation. It's really kind of a unique thing, and it's really a powerful tool that sort of predates the idea of some of the overlay functions, in that it's pretty versatile. It has some problems, but it does remedy a lot of situations. Essentially what happens is it associates attributes based on spatial positioning and interactions and things like that. When you employ a proximity or nearest option, for example, in a spatial join, a record for each feature in a source layer's attribute table is appended to the closest given feature in the destination layer's attributes. So the attributes of the one data set, the closest thing in that one to the thing in the other one, gets joined together. But there's all kinds of different verbiage for how to do the join. Is it something that is the closest? Is it something that contains something? Is it something that intersects something? There's lots of different ways you can phrase it that'll control exactly what it is that it attaches. Now, there's sort of two problems with it. One is you have to maintain that one-to-one relationship. You can only join one attribute to one attribute. And so if you have a bunch of attributes and you want to join a single attribute to all of them, then it still works because individually you're looking at one attribute to one attribute. There's just multiple ones that you're doing it to. But if it's the other way around, where you're joining a bunch of stuff to a single thing, the only way that works is if you summarize it or go to a more traditional overlay type function, because a spatial join just simply can't do that. So one of the problems with overlays, because they're not perfect, is sometimes we have some errors that pop up because of it. And the first one we're going to talk about is something called a sliver. A sliver is a narrow gap formed when a shared boundary of two polygons don't exactly meet like they're supposed to. So you've got two things that should be exactly the same and one's off a little bit, and so spatially you end up with a tiny little thing in between. And so the way that we control this is something called cluster tolerances. And it's a setting in the geoprocessing that we're doing where if two vertices are so close together, it just sort of makes them go together for the purposes of what you're doing. And the good news is you can control what that distance is. The bad news is you can control what that distance is. Turns out figuring out that magic distance is, it's like so much harder than what Goldilocks had to do when she was at the Three Bears cabin. And I think the bears get a bad rap in that story, by the way, because, I mean, technically it's not what Goldilocks did, breaking and entering. I mean, just saying. Anyway, when we look at cluster tolerances in your control over it, if you set the tolerance too large, it will corrupt your data sets and generate inaccuracies where previously they didn't exist. And if you set your cluster tolerance too low, it will fail to prevent the creation of slivers. And the only way you find that spot where it's just right is to find where it's just right. Error propagation is another problem with overlays. When inaccuracies are present in an original input and overlay layers are carried out, those errors propagate through those output layers, and you may not notice that they're there because of any number of reasons. And so you have to be cautious. The more things that you're bringing together, the more opportunities you're generating for continued, repeated, build upon error.